Let's talk now about the normal distribution. And let's take a look at a quick introduction here of some of the properties for the normal distribution. First of all, like usual, let's look at the learning objectives for this particular segment. We want to convert values of a non-standard normal random variable to values of a standard normal random variable, which obviously means we need to define which both of those random variables actually are, a non-standard compared to a standard normal. We need to be able to compute probabilities associated with both the standard normal and the non-standard normal random variables. And we want to compute percentiles for normal random variables. Okay, let's look at some properties of a normal distribution. The normal distribution is our first continuous distribution. In comparison, when we worked with the binomial was discrete. Okay, remember the definitions for discrete variables versus continuous? Well, this distribution, the normal, is based on a continuous variable. The normal distribution is a bell-shaped curve. We looked before at shapes of distributions. We said, well, it looks mound-shaped or possibly bell-shaped. Well, the normal distribution is what actually creates the famous bell curve. The bell curve, well, that's not a very good bell curve. Let me try that again. That's a little bit better. That is the normal distribution. Now, the total area under the curve, if I were to add up all this area underneath this curve, the total area is equal to 1. All right, which we're going to associate the idea of probabilities with area under curve. Because you know, if we add up the probabilities for all the outcomes, like in a binomial, we add up all the probabilities across the entire sample space. For a binomial, it equals 1. Well, it's the same thing here on the normal distribution. Only in the normal distribution, we're going to be looking at area under the curve and attaching that or associating that with the idea of probabilities. Now, these tails that go out like this tail here that goes that way and the one that goes that way, they actually extend all the way out to plus and minus infinity. Now, if I were to take a look at this tail right here and I zoom in on it, the tail's going to look kind of like this. Get really, really close to this line. If I zoom in on that piece right there, that tail is going to look like this. Get closer and closer and closer to the line. If I zoom in right there, it's going to look like that one. I can play this game forever. If you recall from your algebra or possibly pre-calculus, asymptotically is a term that we use. The curve asymptotically goes to 0. Asymptotically goes to the horizontal axis, which means it never touches. It just, as it goes out to infinity, it gets infinitely close, but never, ever, ever actually touches. The distribution is centered at the mean, mu. I shouldn't say the mu. I should say the mean, which is mu. And since the distribution is bell-shaped, hence it's symmetric, we find that the mean and the median, median are equal. This is saying that mu equals theta. Guys, this is a theta. It's not a 0 with a line through it. It's theta. You recall that from the population parameter, the symbol we use for the true median. Probabilities are associated with the area under the curve, as I said a moment ago. The probability of value is observed between any 2 points in the distribution is equal to the area under the curve between those 2 points. So, in other words, if this is my curve that I'm working with, and here's the mean right down the middle, whatever the value happens to be, if I want to know the probability of observing a value between A and B or from A to B, that probability is going to be the same as the total area that's under the curve in between A and B. Now, let's do one more thing on this. This is kind of cool. Because this is continuous, the probability that I'm going to say x, use x as my normal random variable. Say probably x equals exactly some value of A equals 0. Now, in a binomial, we would calculate that out and say, well, it has some probability. It may be extremely small. But in any continuous distribution, it's 0. The reason being and this is actually kind of cool. If we think of the probability from A to A, that's it. It's just the area under the curve at this line. But a line is infinitely thin. It has no mass. It has no width. Okay, it does on paper or on the screen here because we have to. Our pen has to have the width so we can see it. But there's no width there, no mass to it. So the probability is 0. Now I don't want to get into calculus too much, but give you a quick preview of calculus for those that haven't been there. Here's basically the idea of what happens in calculus. If we have a curve like this, and we say I need to estimate the area from here to here, find the area under the curve, what we do in calculus is we say, all right, I'm going to make this into a bunch of boxes, a bunch of rectangles. Now, we all know how to take a rectangle and find the area under the curve. It's simply the width times the height, right? So in calculus, that's what we do. There's a method to say, hey, I'm going to take all those rectangles, and I'm going to use an infinite number of them by taking the width of the rectangles and letting the width go to 0. Not equal to 0, but goes to 0. So that's going to have this infinite number of boxes there, which actually gives me the area under the curve. So when you think about the area associated with a rectangle, it's length times width. So if I tell you this is 0.2 high and 0.1 wide, 0.2 times 0.1, 0.02, you say, okay, well, that's how much area is there, right? But what about here? My length may be 0.2, but my width equals 0. So length times 0, the width, is 0. So there's no area there, no probability. Now, don't get that confused with something that you're trying to model. As an example of a person's height, we can model a man's height as being approximately normal. So you say, okay, what's the probability you get somebody at 5'7"? You say, well, it's 0 because it's continuous. They say, well, no, I know a lot of people that's 5'7". No, you don't, actually. We report ourselves as being 5'7", but if you recall, height is a form of length, and length is a continuous variable, and it's infinitely long. So if somebody says they're 5.7, they're not truly 5.7. They could be, are 5'7". They could be 5'6.99999999377599999 forever long. So in a way that does make a lot of sense. We got to be careful not to confuse the way we talk and the way we think with what actually happens in nature. Okay, the standard normal. The standard normal distribution is a special normal distribution, and that the mean is equal to 0. And the variance is equal to 1. If the variance is 1, then the standard deviation is 1, correct? Because the standard deviation is just the square root of the variance. If it's a standard normal, both of these have to occur. If I have a normal distribution with a mean of 0 and a variance of 6, it's not a standard normal. Likewise, if the variance is 1, but the mean is anything other than 0, maybe 23 or something, then it's not a standard normal. It has to have both those conditions. If the mean is 0 and the variance, hence standard deviation, is 1, I don't care what you're talking about, that is, by definition, a standard normal distribution. The empirical rule, which we have come to love and adore, is based on the standard normal distribution. With a mean of 0, remember the empirical rule says if I go one standard deviation from the mean, I'll get approximately 68%. Well, with a mean of 0, if I go one standard deviation from the mean, that means I'm at -1 and 1. So if I took a look at the area under the curve between -1 and 1, based on the empirical rule, that should give me 68%. Or actually, the empirical rule says about 68%. So it should give me approximately 68%. Go out 2 standard deviations, -2 to 2, and that should give you about 95%. Go out 3 standard deviations, and you should get about 99.7%. Any normal distribution has a mean other than 0, or a variance other than 1, is called a non-standard normal distribution. A non-standard distribution. Okay, that's basically it for the introduction. And I believe next we're going to take a look at some scenarios, look at some notation, scenarios, and actually start using the normal distribution to calculate some probabilities.